Hi, this is Mrs. Basin, and today we're going to talk about rate laws. So a rate law is an expression that shows us how the rate of a reaction depends on the concentration of the reactants. So if you want to speed up or slow down a reaction, you can look at how changing the concentrations of the reactants affects the rate. So the rate constant is something that's part of what's called the rate law. So the rate law is what's in the box there. So the general format for the rate law is rate equals K, reactant 1 to some power, reactant 2 to a power, reactant 3. It can have as many reactants as that particular reaction that you're looking at would have. So the rate constant is the K value. So this is a proportionality constant for a rate law at a specified temperature. So a lot of times when you do these problems, you'll see a temperature given with the rest of the data. For now, we don't need to worry about the temperature. That's just a reminder that all of these rates are temperature dependent. So if you change the temperature, it's going to change the rate of the reaction and thereby change the rate law. So then the order, which are the exponents here, so the x and y in this case, it's a number that expresses how dependent the rate is on the concentration of a reactant. So different numbers mean different things in terms of how that rate is affected by a change in the concentration. So again, the reaction order are these values here, and when you're solving or when you're setting up or working through a rate law problem, one of the first things you'll do is you'll solve usually for these reaction orders. So this is how the order is related to how the concentration, changing the concentration changes the rate. So if something is labeled as zero order, that means changing the concentration of the reactant is not going to affect the rate of the reaction. So if you're trying to speed a reaction up, if a reactant is zero order, changing the concentration of that reactant is not going to have an effect on how fast or slow the reaction is. If something is first order, then if you double the concentration of that particular reactant, the rate will double. If something is second order, if you double the concentration of the reactant, you're going to quadruple the rate of the reaction. So when you're looking at this, like I said, the first thing you'll probably have to do is solve for the order of the reaction. Then it might also ask you for the overall order of a reaction or the overall reaction order. So all you would do for that is you would add up all of those exponents. So once you've solved for all of those, then you would add those up. Okay, so the best way to do these is to do some examples. So we're going to do the example that's in the notes. So this example 4.2 is what we're going to start with. Then I'm going to work through a couple examples from your practice that's in your packet. That way, if you want to see a couple more examples before you start working on these on your own, you have that available. So this is the example that's given in the notes. So it gives us the reaction between nitrogen dioxide and carbon monoxide. And when we're looking at rate laws, all we're concerned with are the reactants. So when you write out a rate law, you're only going to be concerned with what's happening with the concentration of the reactants. The other thing that has to be given in order for you to do or come up with a rate law for a given reaction is you have to have some data and some experiments as to what happens when you change those concentrations. So these data tables will be given. Now, most of them are labeled like experiment 1, experiment 2, experiment 3, etc. I'm going to go ahead and label this one. So when we do some calculations, you can kind of see where they came from. Okay, so there's two ways to do this. The first way is what we call by inspection. So what that means is you're just going to look at the data, and based on what you see, you can identify what the different orders are. And most of the ones that we do, you'll be able to do this way. If you don't like that way, there's also a mathematical way. Now, for some problems, you're going to be forced into the mathematical way, but for a lot of them, you'll be able to do them by inspection if you want to. If you would rather always do the mathematical way, then you can do that as well. So I'm going to show you both ways. So when you're looking at this, the first thing we want to know is what is the rate law for the reaction. So the general format, again, for a rate law is always rate equals K. And again, K is the rate constant, and we'll solve for that after we have a rate law. And then I'm going to sub in the reactants, if I know what they are, and then give them exponents. So NO2 to the X, and then CO to the Y. If there was a third reactant here, then I would have to add that third one on. So when we're looking at what the orders are, we have to pick two experiments where one changes and the other doesn't. So if we look at these first two reactions, experiment 1 and experiment 2. In experiment 1, NO2 is doubled, but CO stays constant. So that means anything we see in regards to the rate was a result of what we did to the NO2. So if we doubled the NO2 and the rate increased by a factor of 4, then by definition, that means that this X value is going to be 2. So that means it's second order with respect to NO2, or NO2 is second order, or a second order reactant. Okay, so that's how we would do that by inspection. We're going to do the same thing for CO. For CO now, we're going to look at experiment 2 and experiment 3, because NO2 stays constant, but CO doubles. So NO2 is constant, CO doubles, and nothing happens to the rate. So we've doubled the concentration of CO, held the other one constant, and the rate stayed basically the same. So again, by definition, that means the Y value, or the order of CO, is 0. Okay, so that previous slide, those are the definitions we have to know to be able to assign these rate orders to the reactants. So again, we would say that CO is 0 order. So again, what that means is if I change the concentration of CO, it's not going to affect the rate. Now, CO still has to be present for this reaction to occur, but changing that concentration is not going to have an effect on the overall rate of the reaction. So then by knowing this, then I would rewrite this as rate equals K NO2 to the X, which is 2, CO to the Y, which is 0. So if this is Y to the 0, that equals 1. So that means the CO is not going to be included in the rate. So the rate law for this reaction would be rate equals K NO2 to the second. Okay, so then once we know that, then we can use any of these reactions or any of these experiments that are provided to solve for K. So to do that, I'm going to use just this first one. So I'm going to sub in the rate that's given, so 0.0021, so that's the rate. K is what I'm trying to solve for. And then the concentration of NO2 is 0.10 for that particular experiment to the second. So I'm subbing those values in from that experiment, and because K is constant, you could use any of those experiments that are provided. And then I'm going to solve for K. Now, the only thing weird about this is K is not always going to have the same unit. So the unit of K is going to be determined by the overall rate of the reaction. So in this case, the overall rate of the reaction is 2. So this is a second order reaction overall. So to calculate this, we can actually do this mathematically. So the rate is always going to be molarity per second. So that's the unit for rate. Concentrations are always going to be molarity. So if I square that, that's going to be molarity squared. So when I solve for this, that molarity is going to get rid of this molarity when I do the math with this, and I'm going to end up with 1 over molarity seconds. Now, the other way you can write this, if you remember we've written this before, is m to the negative 1, s to the negative 1. So the unit for K is actually these values here. And as we work through these, we'll talk a little more about those units with K, but just know that the unit for K is not always going to be the same. The unit for rate is not going to change for a given set of data. The unit for a concentration is not going to change. But when you're writing the unit for K, it's going to depend on the overall order of the reaction. So for a second order reaction, the units for K are always going to be m to the negative 1, s to the negative 1. So my final answer here would be, when I solve for this, it would be 0.21 m to the negative 1, s to the negative 1. So that would be my value for K. Okay, so I'm going to go to this next slide, and it still has the same data, but this time we're going to do this mathematically so you can see how this would work if you don't want to do it by inspection. So we're going to do the same thing here. So we're still going to use those same two equations, or I'm sorry, those same two reactions. So for this first one, I'm going to use experiment 2 and experiment 1. I keep calling them reactions. They're different experiments. So, or trials, experiment 2 and experiment 1. And I'm going to, again, use that general format for the rate law. So the general format for the rate law is rate equals K NO2 to the X, CO to the Y. Okay, so when you set this up, we are going to take the two experiments and put one in the numerator, one in the denominator. Now, it doesn't matter which one you put where, but one is going to give you easier math to do. So I'm always going to put the one with the larger rate on the top. So in this case, I'm going to set this up with experiment 2 over experiment 1. So then I'm going to sub in the values for the rate law that I wrote here. So the rate for this experiment 2 is 0.0082 equals K. I'm going to sub in the value for NO2, which is 0.20 to the X, and then the value for CO, 0.10 to the Y. And I'm going to put that over experiment 1. So the rate for experiment 1, 0.0021 equals K. The value for NO2, which is 0.10 to the X, 0.10 to the Y. So then K is going to cancel, the Y's are going to cancel, so now I'm left with something with only one variable that I can solve. So if I take this 0.0082 divided by 0.0021, I get 4. And then when I solve this here, I get 2 to the X. So then I know that X equals 2. So again, that tells me that it's second order with respect to NO2, or NO2 is second order. Okay, I'm going to do the same thing for the CO. This time I'm going to pick experiment 2 and experiment 3. And I'm going to put experiment 3 on top because it has a bigger number. So experiment 3 over experiment 1. The rate, 0.0083, equals K. The value for NO2. So this time, and again, I'm picking those two because one of the two substances canceled out. This time I'm trying to find CO, so that's why I picked those two particular experiments. So 0.20 to the X, 0.20 to the Y, over 0.0082, and again, this is coming from experiment 2, equals K, 0.20 to the X, 0.10 to the Y. So same thing happens here. The K's cancel. The X is cancel this time. So now I'm left with 1 equals 2 to the Y. And for something, an exponent to make something equal to 1, we know Y has to be 0. So we got the exact same values as what we got on the previous slide just by looking at it, but this is a mathematical way to do it. So again, you're free to do it either way. If you do it by inspection, you have to be able to justify your answer. So you have to, like if you came up with the NO2 is second order, you have to be able to tell me that it's second order because when the concentration was doubled, the rate quadrupled. If you do it mathematically, then the math is your justification. Okay, so these next two problems that we're going to do, if that made sense and you feel like you know what you're doing, then you can stop the video and start working on the practice. If you want to see a couple more examples, pause the video for a second and find your rate law practice sheet in the back of your packet. And we're going to work through number 1 and number 2 together if you want to see a couple more examples. So I'm going to do both of these mathematically. You, again, are free to do them the other way, but I'm going to show you the mathematical way because for some people that just tends to make a little more sense. Okay, so we're going to do the same thing here where it says I'm looking for the order of reactant A and the order of reactant B. So I'm going to start with A. So what I have to do to find A is I have to find 2 experiments where A changes and B stays the same. So I'm going to use experiment 3 and experiment 2. When I set this up, and I'm going to do these over here so that we have room. So I'm going to put experiment 3 on the top because the rate is larger and that just makes my math a little bit easier here, over experiment 2. Okay, so experiment 3, the rate is, and again, we're using that format of rate equals k, a to the x, b to the y. So I have 32 equals k, 0.20 to the x, 0.20 to the y. And again, this is all coming from the data table here, over 4, because now I'm using experiment 2, equals k, 0.10 to the x, 0.20 to the y. So k cancels, the y's cancel out, so I'm left with 8 equals 2 to the x, so x equals 3. So the order of reactant A is 3. So it's third order with respect to A, or you could say it's order of reactant A is 3. Okay, now we're going to do the same thing for B. For B, we're going to use experiment 2 and experiment 1. Again, because A stays the same now, but B changes. So I'm going to put experiment 2 on top, experiment 1 on the bottom. So for this one, I have 4 equals k, 0.10 to the x, 0.20 to the y, over 2, and again, data is coming from the data table here, equals k, 0.10 to the x, 0.10 to the y. So all I'm doing again is subbing in those values for each of those experiments using the data that's provided. So this gives me 2 equals 2 to the y, because the k's cancel, the x's cancel. So y equals 1. So the order of reactant B is 1. So the rate equation, or the rate law for this reaction, would be rate equals k, a to the third, b to the first. So again, if it's to the first, you have to write it. You don't have to write the exponent for this one. Okay, so this one, it could also ask what's the overall order. So if it wanted to know the overall order, we would add those exponents together. So the overall order for this one would be 4th overall. All right, now it asked me to solve for k. So like we said before, we can pick any of those reactions. It doesn't matter which one it is. So we're just going to use that first one. And I'm going to sub in those values. So the rate is 2.0 equals k, 0.1 to the third, 0.1 to the first. So k for this one is going to equal 20,000. And then like we said before, units are kind of weird on here, so this is going to be molarity per second. Molarity to the third times molarity. So I have molarity to the 4th. So I'm going to end up with 1 over molarity to the 3rd seconds, or m to the -3, s to the -1. So all I'm doing to get that is I'm just mathematically calculating out the units like I did with the math. Okay, so that would be my k value. The other thing that they could have you solve for, and I think in the next example we'll do this, it'll say now that you have the rate law, what if A was this value and B was this value? What is the new rate? So if you have the rate constant and you have any values of A and B, then you can solve for a new rate. Okay, one more. This is number 2. So it gives us the rate data. Again, we're going to do the rate, the order of reactant X, order of reactant Y, overall order, the rate equation, and then go from there. Okay, so again, same deal here. You can do this by inspection, or you can do it mathematically. I'm going to do it mathematically, and then we'll kind of talk through the other way for this one too. So we're going to start with X. So to solve for X, I have to find 2 where X is changing, but Y is staying the same. So I'm going to use experiment 3 and experiment 1, because X changes, Y stays constant. So experiment 3 and experiment 1. So the rate is 4 equals 0.20 to the x, 0.20 to the y, over 4 equals 0.10 to the x, 0.20 to the y. So on this one, The y's cancel. Oh, I'm sorry, I forgot to put the k in there. So the k would be in there, the k would cancel. So I get 1 equals 2 to the x. So I know x is 0. Okay, and this one you'd be able to pretty obviously see that if you change x, nothing's happening to the rate. So you would know that that's a 0 order reactant. And you can also do one of them by inspection and then another one mathematically. So you don't have to do them all the same way. So order of reactant x would be 0. Okay, for y, we're going to use, let's see, experiment 1 and experiment 2, because x stays the same and y changes. So this time I'm going to put experiment 1 on the top because the rate's larger, and then experiment 2 on the bottom. So 4 equals k, 0.1 to the x, 0.2 to the y, over 1 equals k, 0.1 to the x, 0.1 to the y. So k's cancel, x's cancel. So I end up with 4 equals 2 to the y. So y in this case would be 2. Again, we can look and see that y was doubled and the rate increased by a factor of 4. So we know by definition that means that the order is 2. So then the overall order, I would add those up. So the overall order of this reaction is 2. And then to write out the rate law or the rate equation, I'm going to say rate equals k. And I'm going to write this, but then I'm going to rewrite it. So x to the 0 we're not going to include, but I'm going to put it there just so we can kind of follow where it went. So then you would end up with rate equals k times y to the second. Okay, next thing, we're solving for k. So we're going to pick one of those experiments. So I'm just going to, again, pick this first one. So the rate is 4.0 equals k times 0.2 to the second. So k equals 100. And again, to get the value for k, or I'm sorry, the unit for k, I have m squared on one side, m over s on the other side. So that's going to leave me with m to the negative 1, s to the negative 1. And we'll, as we move forward, like I said, we're going to do more work with figuring out how to manage those units for k. Okay, finally, now it says, what is the rate when the x and y are both equal to 0.25? So now what I can do, since I have a rate law, I can solve for new rates given new concentrations. So I'm going to say rate equals, I have a k value, 100. And just to see how this all works out with the units, I'm going to put the units in here too, times 0.25 squared, and this is 0.25 molar squared, that gives me 6.25 molarity per second, or m s to the negative 1. So you can see that when we divide that, that's going to get rid of one of the m's and it'll leave it with molarity and then seconds in the denominator. Okay, so that's another thing you could be asked to do once you have the rate, is what is the new value when you have a new value for a concentration. So do the best you can with these, work through the packet. If you get to the point where you feel like you know what you're doing and you want to move on to the online homework, you can do that if you want to save some of these for a review for later. And then when we come back on Monday, we will do some more review with the rates, check in to see where everybody's at. We might do maybe a live Zoom on Monday just so I can kind of talk to you guys and see how we're doing. But again, at any point during class today, if you feel like you need help or you want to check in or you want me to go over another example problem, just send me a message or an email and I'll send you a Zoom link and we can Zoom and kind of go over stuff if you need help with something.